one.
Okay, hello everybody. Welcome to this week's book club. This is the chapter about linear regression, which is, pretty foundational for all the other approaches in the rest of the book. I think most people probably have some familiarity with linear regression. I was surprised, how much in going over this chapter I had forgotten, and how much maybe I had never learned or was presented in a different way. So I certainly won't get to all the material. I tried to focus on items that I either thought were like quite foundational, like really, important, or maybe that caught my interest or attention. So yeah, and I am trying, as I just said before the start of the recording, I'm trying to sort of go back and forth between the Python and the substantive material, so that like as I introduce, like, here's a one variable, one predictor linear regression, then show that in Python, so we get a little bit of we get our code matched up to our substantive learning. Okay, so yeah, here's just the agenda for the chapter. Just and I think I'm moving through it in a slightly different way than the book does, but I was trying to match kind of the code to the substantive material. But I think for today, we'll certainly cover the basics. I think we'll cover measures of accuracy and fit. So that's going to be like R squared and the F test and so on. And I think probably that will be it. If we get past that, we can go on to the diagnostic strategy. So the strategy that we use to test the assumptions that underlie linear regression. And then they also have some extensions, so like the use of like polynomials on the predictors in linear regressions. There's like a KKN regression that they sort of float as like an alternative, although apparently like a generally sort of like less desirable alternative. So we'll go through those as well. I think probably the next session. Okay, so this is it. This is the core of linear regression. And so the idea behind linear regression is that we assume some kind of like data generating function that has a linear form. And so you could imagine lots of examples. You could like maybe age and height, at least up to a certain threshold. Maybe that's a bad one because height tends to stop pretty quick. But you can imagine your own example. And so we have this idea that there's a sort of like a population function that's generating the data that we are receiving. And so that the key components, and I don't know if you can see my mouse. Can only I see my mouse? I don't know.
If it's white,
whatever.
it's blending in. I don't know.
Okay. All right. Well, never mind. So the key components here are, beta 0, which is an intercept term. So that just determines where the line intersects in this like one variable, one predictor regression that just determines where our line intersects with the axis. And then beta 1 is the more kind of significant term, and it kind of specifies the slope of the line, and therefore like the relationship between the outcome and the predictor. And then epsilon is the sort of at this level, it's like the irreducible error. So there's just some randomness that we kind of can't avoid in the generation of our data. So how do we compute these quantities? We minimize the square difference between the estimated line and the observed values. So just to dwell on that for a second, and you can see this cool figure from the book. And I guess any course on linear regression kind of has this like obligatory figure that shows this line, and then it shows all the observed points, and then it'll show the distance between each observed value and the line. So the distance in this case, or in all cases, are what we call the residuals. So they're the kind of difference between the line that we estimate and the observations, the sample that we have. And it turns out that the best linear estimator, like an unbiased linear estimator, is one that minimizes the square difference between the minimizes the square difference between the observed values and the line. And I just pulled this out of the book because I thought it was kind of a cool chart. But so basically, like algebraically, what we're trying to do is select beta naught and beta 1 to minimize, this RSS value. And you can see they've done it in 3 dimensions, which I think is kind of cool. And so at the minimum is at the bottom of this kind of hammock. And so, yeah, so you're selecting them both in tandem to minimize this RSS value. And I think they go through it a little bit like algebraically in the book. I didn't post it up here. I think we tend not to need those at least in my experience. I don't know, like we tend just to use the computational tools, but that, I think in the univariate case, they are, kind of interesting, and then they get complicated quite quickly. Here we go. Here's my, at least one of my unforced latex errors. But so, yeah, so, yeah, I think I see what happened. So I think what this slide was supposed to articulate is that, so we have hypothesized a population level line, like a true, in some sense, line that defines the relationship between our predictor and our outcome. But we don't ever observe that true line. We only ever observe sort of like an estimate of that line. So we take our observed values and then we try to estimate some version of that line. And thankfully, because of the nice properties of ordinary least squares regression, the estimates of beta 0 and beta 1 are unbiased. And I thought this was a nice figure. I think this is figure 3.3 in the book. And so this is just showing there's a red line, which in this case is the population level line. It's like the data generating function. And we know in this case, because this is like a simulation, all the dots are simulated data from the red line. And then the blue line is the line that we fit from the observed, from the simulated data. So you see that it's not like exactly the right line, but it's pretty close. And in fact, in that second figure, you see that if we were to do many simulations and estimate many lines, we would get kind of this series of light blue lines, which kind of are trying to approximate the red line. And so you can see that, there's variation, but it's an unbiased estimate. Sorry. And so here's another, obviously latex error, but I wanted to walk through, and I hope my next slide works because it's really cool. Yeah, there we go. So there's a couple different ways they kind of like represent this equation in the book. So there's this first kind of most basic way, which is where you represent the equation on like a per observation basis. So you can see like y is subscripted and x is subscripted. So as you move through each observation, you're kind of pairing the right x with the right y and the right epsilon. In the multivariate case, we do the same thing, but we just add another predictor. So in this case, z, and we just it's just to make sure that we're pairing each predictor with each observed outcome and each error term. And then like if we want to generalize like the most, we can move to this kind of like matrix algebra representation, which just has a matrix of predictors, a matrix of observed, like the observed values of the predictors, and then matrix of the outcome and matrix of the error term. And so I kind of broke that out because this ends up being important to how we do this in Python. So so you can see we have like an n times p, so n being the number of values, number of observations, and p being the number of predictors. We have an n times p matrix of kind of observed predictor or observed covariate values. We have a matrix of like our betas, so p times 1 is the number of predictors. And then we have a matrix of our error terms. Again, every every observation having its own error term. So the reason that's important is this first matrix here, the n times p matrix that specifies the values of the covariates, is called like the model matrix or the design matrix sometimes, and it kind of ends up being important to how, at least in the lab section, they kind of execute these regressions. And so you can see the way that we can set up like a simple univariate regression in Python is to just use pandas. And I don't know, you know, this was news to me. I'm still learning all this panda stuff, so we can, I guess, feed pandas a dictionary with the, you know, the column name as the key, and then the value in this case being a series of ones, or the this is a data set from the book. I think I'm not sure what LStat is, but it's something related to Boston real estate prices. And so that will actually, you know, so that will create that matrix that we saw on here, where we have a column of ones and then a column of, in this case, you know, x1, which is LStat. And you can see it printed out here. We have the column of ones in the intercept column and the predictor value in the LStat column. And in case it's not, I mean, I think everyone knows this, but in case it's not obvious, you need the column of ones to pair with the intercept term. So because, you know, there's no observed value to pair with the intercept, but when you do the matrix multiplication, you want beta naught to pair with the column of ones, in case that wasn't obvious. So yeah, and then the kind of remainder of the workflow is to fit, you pass your model matrix to this function from the SM, the stats models package. And so I don't know how, you know, I don't know, we can talk about this. Like, is this like a commonly used package, or is this something that only the book is kind of recommending? I'm not sure. But so you can pass your model matrix to the OLS function here. I'm sorry, I've got some formatting errors there too. Something quite catastrophic happened. I did this paste and then it just really like reorganized my whole document. I'm not sure what exactly happened, but so yeah, you can generate this kind of model object from the OLS function, and then you can obtain the results with the fit method of the model object. And yeah, I did want to ask anyone who is familiar, like, is this a common workflow, and in particular, the use of this stats models library or module, or is this just sort of unique to the book? I'm not sure.
This one, from what I know, this one is very classical.
Okay, that's good. That's useful.
Yeah, I think you don't see it very much, but it's not just part of the book.
Okay.
I think most people just do sklearn for anything almost now,
yeah.
classical ML, or like Torch or whatever for the more advanced stuff.
Yeah. Got it. Well, I have to apologize about my my botched stuff here. It really, like, before I did the paste, everything, I don't know. I apologize. But so yeah, so this is related actually to the sklearn point that you just raised. So when we create multivariate models, we need multi-predictor model matrices. So instead of just kind of like stacking those up ourselves in pandas, we can use what's called a transform object from, in this case, we're using a package from the book called model spec, but the book kind of implied that maybe that was part of the sklearn workflow. I don't know.
Okay. Sorry, if I may, because I went on GitHub to look at the package. So it's a specific package. It's a complex one, but basically it's exactly what you mentioned at the beginning. For us, at the beginning, it's just a way to have your matrix design. I really like the way you present at the beginning, because the MS object is it's just going to do what you present at the beginning. We need the matrix with the first with the intercept and LSAT at edge, and after it's just a matter to fit an object. So at least if you make any change in any data set, you are just going to reuse the design. So it is a very great presentation, but it is something that I have never seen before, because the ESL package is really specific to the book.
Yeah, I agree. I like this, and so I guess this slide, even though it's kind of jumbled, this bottom code block, you can see this design object, or excuse me, the transform object is really useful because it has this like two-step workflow where you call fit on your object, and that I think can apply different pre-processing techniques. And so we didn't do that in this chapter, but it seems like maybe you could call that to do maybe some like scaling or centering or other forms of pre-processing on the model matrix, and then you call
and then you call sklearn, in sklearn, the fit transform, it's always something that we do all the time. Fit transform, it's a very classical in a lot of the sklearn models, fit transform.
Okay. Yeah. And then, exactly. Yeah. So the transform, I think, applies that pre-processing. And so that seems like a cool workflow to me. It seems like that is a more reproducible workflow, since you're always if you change the data, you don't have to recreate the matrix. You just have this kind of series of functions that does it for you. So I think that covers just this basic part, this sort of introduction to the basics of linear regression. And then I wanted to jump into these different measures of accuracy and fit. So the one that we're probably all familiar with, this is more of a measure of accuracy, although I'm not sure that's even the right kind of concept for the standard error. But so the standard error is the standard deviation for each of our estimates of each of the different parameters. So in the case of beta 1, we can see that it's equal to this function of the residual standard error, which we can kind of think of as the standard deviation of the residuals and the covariate values on the bottom in the denominator there. And so the standard error is really important. We use it to conduct confidence intervals, create prediction intervals, and do hypothesis testing. And I thought I would dwell here on this kind of classic tortured kind of definition of confidence intervals, which is that a 95% confidence interval is defined as a range of values such that with 95% probability, the range will contain the true unknown value of the parameter. And so I think the point here is it doesn't equate to the kind of more colloquial meaning of a confidence interval, which would be that you have 95% confidence that the value is in some range. Instead you have 95% confidence that I don't know, I have a hard time even articulating it, that you've selected a range that contains the true value, something like that.
Okay.
I wonder if it's worth pausing. Yeah.
I don't recall the exact wording, but it's more like that. If we are drawing 100 times from the same population and do the same analysis, in 95% of the sample, we will get the value inside.
Yeah. Yeah. And that, that's related to the fact that we're our line itself is an estimate of from a population. So our confidence intervals too are the product of a sample and not sort of estimates for the whole population. Gosh.
Do So just to not to try not to skip ahead, but do we go into later the standard error of the different parameters like beta 0 and beta 1?
So I haven't broken out the math for, obviously I have beta 1, but we could go into that if you want. Like, and I'm so frustrated. Like 10 minutes before I pasted this chunk into this bit about hypothesis testing. I don't know what it did. It messed up my whole presentation. So I'm very sorry. Like,
don't worry about that. It's still visible for us.
Yeah, oh my gosh. And then the slides are I don't know, whatever. So in Python, the confidence intervals are very easy to create. They're kind of the product of they're I believe a method that you can call on the results, the sort of fitted model object, the results object. And I originally had a slide about prediction intervals, which are kind of over here, but we might also want to create confidence intervals for our for the values that we predict. So say we take new data and put it into the model and generate predicted values. When we do that, we want to add an additional source of uncertainty to the estimated confidence interval, because the predicted value has to kind of contain both uncertainty about the choice of model and uncertainty related to sampling. So that's kind of like, it has to have both reducible error and irreducible error kind of incorporated into. So that's what this was meant to illustrate, is that when you use Python to generate these prediction intervals, you get much wider intervals than you do with a standard confidence interval. And so, yeah, this just goes through the standard hypothesis testing workflow. I'm trying to think how to. Yeah, I think most people will be familiar with the hypothesis testing workflow, but the core idea is you're posing a null hypothesis and an alternative hypothesis. The null hypothesis is typically that the value of beta 1 or whatever your kind of parameter of interest is 0, and the alternative hypothesis is typically that the value of beta 1 is not 0. You then use your observed values to estimate the probability that you would have observed those values by chance had beta 1 been 0, if that makes sense. So oftentimes you'll see, well, if you have a real relationship on your hands, you'll see that your observed beta 1 is sort of 2 standard deviations or more away from the 0 beta 1. The p-value, and sorry, I'm kind of garbling this up a bit, but so the sort of customary way to describe this idea that we want a beta 1 that we had 95% chance or more of not observe. Excuse me, I'm getting quite mixed up. We want a beta 1. We want an observed beta 1 that we had a less than 5% chance of observing if beta 1 was 0. Right. Okay. And so the customary way to describe that is with this p-value. So p just corresponds to 0.05. Maybe they use different values in some other contexts. But yeah, so the customary one, at least in kind of, yeah, I think in general, social science, it is 0.05. Maybe in sort of higher precision domains, you'd use a lower p-value. And oftentimes we say that like if something has a p-value less than 0.05, it's like a significant finding, although that's like maybe ended up being quite a problematic choice. I think we saw even in this chapter that sometimes single parameters can be significant on their own, but not significant when used in combination with other parameters. Yeah, so it has kind of its, it ends up having some effects on like the scientific enterprise as a whole, the choice of this kind of p equals 0.05 value.
You know, here, Cory, sorry.
Yeah, go ahead.
Before we move on, I was just wondering what people do think about the 0.05 threshold and like the replication crisis in social sciences and what's been happening. Seems like this convention is like, apart from just outright fraud, this convention of it almost accepting a 0.05 shows that there's something happening is like responsible for a lot of bad outcomes or bad science.
I'm just jumping in on that actually from what you said, Jack, because obviously I did psychology, I did cognitive psychology, and that was a massive issue with some of the conclusions we would make, either in trying to obviously build our own experiments and write our own papers, but also when we were actually trying to understand some of the theories, because like as Jack said, the replication crisis in psychology, it's become so fraught. Especially with some of the more sociological theories rather than computational. So like some of the stuff you'd read another paper, and then you think that doesn't make sense, and a lot of it doesn't add up, and it's causing a big issue, at least in psychology. So from personal experience, I can say that the p-value is definitely like a massive culprit in creating a lot of problems with theories. And I think that's why a lot of psychologists now are veering towards like more Bayesian theory and probabilistic reasoning as a result, because they're realizing, well, actually, like we're trying to find a causation where there is none, and potentially hypothesis-based reasoning in social sciences is meeting this issue and is having to deal with it. Sorry for segueing, but I thought like just because it was relevant when I saw that and read that in the book.
Oh, I think it's good stuff to think about. Oh, sorry, Sandra.
Another point is that when you are running hundreds of tests, you are not using the p-value, then after you use the q-value to be able to just, because if you do 100 times, at least statistically, you are going to find some p-values are under the value. So it's, yeah, we could open such a mess because after the p, we have the q, and maybe there will be something else.
Yeah, I mean, p hacking is probably, it's not even necessarily malicious, right?
No,
it's like a researcher with good intentions tortures the data forever and finds some effects that look to be significant. I suppose as well, there's the problem of n. It's like if you make n really big, like your tiny differences are now going to be considered like statistically significant, but maybe in real terms, the actual difference is completely irrelevant. But you go searching for this p-value. It seems like
actually that's again when I was reading that in this chapter. Sorry, my internet. I don't mean to interrupt, but it was the disparity between p and n was exactly some of the issues we had in loads of papers when they would do loads of qualitative interviews with people, and they'd say, oh, the number of candidates in this experiment is huge, it's like 34,000, and so clearly, look, we've got this big effect size or this really low p number, and when you look deeper into it, it's quite meaningless.
Yeah, I think my sense, people are dissatisfied with the p, the use of like the significance testing to basically like determine whether or not something is worthy of being published. I think that's the kind of crux of the problem, is that only the significant findings get published, and so all the 95 other studies that didn't get a good sample don't get published. People, I think, have some dissatisfaction with that. Like, I think we are seeing like where they'll show like a Bayesian kind of like posterior distribution or whatever. Although I also don't see too much published that doesn't. I think usually there's a part in the paper that's like, oh yeah, by the way, we did meet the 5%, threshold. Even if they're doing like a Bayesian interval or something like that, and people still have that kind of hunger for the kind of significance level. So yeah, I don't know. I don't feel like a good replacement has arisen, or like a good kind of alternative. But yeah, there's definitely some dissatisfaction, I think, with the use of it as kind of like the ultimate arbiter of whether something should be published. Yeah,
I'm
maybe
sorry for
that,
derailing, because I think it's actually such a deep or wide conversation, isn't it? That it could go on for a long time.
yeah,
Interesting stuff.
I think it's also very interesting. I don't know what, maybe just every review has to be more kind of holistic.
Because you need to publish
Yeah.
negative results as well, or there needs to be incentive
exactly.
to publish negative results, because then you're going to unearth more attempts at p-hacking and whatnot. And you need to care more about the effect size or a different statistic than the p-value. But yeah, all pretty interesting stuff.
Yeah. So yeah, there's that. So yeah, the next kind of measure, so the standard error we can think of as like a measure of accuracy. The next kind of big measure of fit that we're most interested in is the standard deviation of epsilon, or the residual standard error. And this is kind of used as like a heuristic to assess the absolute measure of the lack of fit of the model, which I think makes like a lot of intuitive sense. And so if you think of the residual standard errors being expressed in the units of the outcome, whatever sales or whatever you care about, if they're like all over the place, then you maybe have some concern that your model isn't fitting the data very well. Here's the formula for residual standard error. And yeah, so again, we can see like it's just the square root of the residual sum of squares adjusted for sample size. So yeah, I think, I don't know that I have much more to say about the residual standard error. Does anyone have anything to add to that?
I think that we just have the two, because there is two. It's a degree of freedom, so maybe just because we have one variable. So if we have more driver, we would have P. Just be careful about that.
Yeah, I'll fix that when I kind of try to push it to GitHub or whatever. Yeah, and the next kind of famous measure of fit is R squared. So R squared is trying to measure the variation in the outcome that's explained by the model. So you can see and so it is like literally just a fraction. So we have the residual sum of squares over, I think, the total sum of squares. So you're, again, just two measures, basically a variation, and then some creating a fraction, and then subtracting from one. So yeah, this is basically, I think there's no simpler way to put it than that, like the proportion of variance in Y explained by using some predictor X. So this can be a useful heuristic. It has a problem in that as you increase the number of predictors, even predictors that are irrelevant, you'll get higher R squared values. And so you can kind of artificially inflate the value of R squared just by adding more and more kind of useless predictors. And that does kind of really undermine its usefulness in kind of these multivariate regression scenarios. I think, again, it's a little bit like the p-value where people are wary of R squared, but they still like to have a high one. I think there's maybe not a good, and so there are also various, like there are some adjustments you can make to R squared to account for the number of predictors. And then we also have other ways to, so like the F test, which we could use to basically assess like whether or not a predictor should be included in our model, whether or not it's adding anything to our model. So in Python, both of these attributes are stored in the fitted model object, and you can just access them very simply and easily. And let's see, I think that's where my slides run out. Although I would like to do F squared. I might stop there. Just sorry, I'm a bit frazzled because of this the formatting difficulty. But yeah, I think I'll stop there, unless we want to dive into F squared. I feel like maybe we could use the old slides, I guess, if we wanted to. But yeah, I think my plan for next time would be to go through, try to cover the exercises, at least the exercises that are the most interesting, and then yeah, to start off by covering the F test and the diagnostic strategies for assessing like whether or not you have your residuals are kind of independent of observations, whether or not you have like collinearity, all this stuff. So yeah, I think that's it.
Yeah, great. I think stick a flag in it for this week to pick up the second bits next week. I will stop the YouTube